Okay, so we have derived dimensionless equations, three dimensionless differential equations uh, for R, W and G prime, where just to recall it quickly, R is the radius of the plume, dimensionless radius, W is the dimensionless vertical velocity, which is the mean velocity of the plume, and G hat here is the dimensionless reduced gravity of the plume, and that's again is the mean reduced gravity at a particular height Z. Okay, so we have three parameters and three equations to solve for these parameters. So we will try to find a solution now. And what you see here is there is one constant apart from R, W and G. We also have A, which is a dimensionless number. That's the entrainment coefficient, which we have seen before. So A is the entrainment coefficient, and its value is 0.125 found experimentally. Okay, so this value A is equal to 1.125. This cannot be predicted theoretically, it can only be found experimentally, and this is the standard value that has been verified by many experimentalists who work in the area of fluid dynamics, particularly focusing on plume flows. Okay, so now to find a solution to these three set of governing equation, A hat, B hat and C hat, and why we are calling them hat, just because they are dimensionless equations. So to this, obviously we also need some boundary conditions. So one of the boundary condition here is that radius, we assume the radius R is equal to 0 at Z equal to 0. Okay, that is the dimensional radius of the plume and Z is the dimensional height. So this actually gives us R hat is 0 at Z hat at 0. So this is one of the boundary condition we have, and for the rest of them, where G hat and W hat, so W hat is not 0 at Z equal to 0, and also G hat is not 0 at Z hat equal to 0. So we don't know the values of W hat and G hat, we only know the value of R hat. So we have three equations, but we only have one boundary conditions, one known boundary condition, right? And that's why we use trial and error method to find its solution, and we solve this problem numerically to derive a solution. Okay, and this solution that you see here is a numerical solution that is derived using the given boundary condition and trial and error method. Numerical solution where A is assumed to be 0.125. Okay, and what do you see here? This particular equation shows you different parameters. So the red one here is R hat, that is the dimensionless radius R. This buoyancy that you see is actually not really buoyancy, that is G hat. So it is written as buoyancy, which is equivalent term, but this particularly G hat. And this vertical velocity is W hat. And the vertical axis here is the Z hat, that is the vertical height. Okay, and what do you see in this solution? There are few interesting things. First is that the radius of the plume as you go from the injection point. So we are assuming that this is value 0, where the plume was injected at z equal to 0, right? And radius here r equal to 0 at z equal to 0, right? So that is the boundary condition we have also used, and you can see how radius continuously increases, but there is a point around here which is the value is around 3.8 here. You can see how radius increases with a high rate, right? Until there you can see it is increasing linearly, but all of a sudden the rate with which radius increases is much higher than before, right? And in fact the radius just keeps increasing without going any further, right? And that is the point where also you can see the vertical velocity w becomes 0. So this is where this you can say is the initial vertical velocity which is considered. Okay, so this basically at z equal to 0, this is considered to be infinity. If you go further, this actually is assumed to be infinity. So that is actually another boundary condition which we were avoiding. So w is tends to infinity as z at z equal to 0, right? But obviously we cannot define z as infinity, and that's why we just considered that as an assumption. Okay, so w hat is extremely large at z equal to 0, and you can see as we go up or away from the source, w hat decreases or the plume velocity decreases, and then there is a point, this around z hat at 3.8 when your vertical velocity becomes almost equal to 0, right? So at z hat equal to 3.8, w hat is equal to 0, and r hat tends to r max. Okay, and r max is something that is not the exact value, it just keeps expanding, right? Because you're continuously injecting fluid, so radius, it has to go, that injected fluid has to go somewhere. So instead of going further up, it actually starts spreading sideward. So and in fact we can say r max tends to infinity, okay, because here this can just keep going to infinity, okay, if you continuously inject a buoyant fluid at the bottom. Alright, so that is the radius of the plume, and vertical velocity becomes 0. That means your plume ceases to go up further, and that's why it takes a halt at that point, and it just flows in the sideward direction, in the horizontal direction, instead of going vertical direction. And that is why there the horizontal velocity becomes important instead of vertical velocity. Okay, and another thing that you see here is that g prime value, g hat, it also started with some value here which must have, it may also be going to infinity at z hat equal to 0, but what's happening is, so this is the direction, this is actually decreasing as we go further from the source, but there is a point here when it becomes almost equal to 0, and that value, so at this point z hat is 2.9. So when z hat, that is a dimensionless number, 2.9, your g prime or g hat becomes equal to 0, right? So we see that g hat is 0 at z hat equal to 2.9. all right, so that means your buoyancy or the temperature difference or density difference between the plume and the ambient becomes 0, because z hat is equal to 0 means your delta rho is 0. That means so this leads to delta rho 0. That means the buoyancy force is 0 at z hat equal to 2.9, right? but we still see that there is an additional height that is being covered here, right? So from this point till this point, even if buoyancy force becomes zero, plume continues rising, it's still going up, because maximum height it reaches is 3.8, not 2.9, and that is happening because the plume still has some momentum flux. Even if the buoyancy flux becomes zero, the temperature difference, density difference, or concentration difference between the plume and the ambient becomes zero. It has gained this vertical velocity, right? And that vertical velocity is this value, right? At this point, this is W hat, which is not zero, right? So that vertical velocity is providing momentum, right? So that momentum flux or inertia force is there, that is actually driving the plume upward, and that is why this delta Z that you see here of 3.8 minus 2.9, that delta Z is covered by this momentum flux, not buoyancy flux. Okay, and as you go further up, obviously the G prime goes negative, and then the momentum becomes zero, and beyond that point there is no force for plume to drive further up, and that is the point at 3.8 plume completely stops. Okay, so this is a solution that is derived numerically for value of A as 0.125. In this particular solution should work for all plumes in stratified medium, because this is a dimensionless solution. And now by using this dimensionless solution, we can actually predict what is the dimensional solution of the plume. Okay, because we now know the value 3.8 or 2.9, etc. We can also from here predict what is, let's say, the vertical velocity. When this becomes zero, it looks like this is roughly equal to 1.2, I guess. So this may be equal to 1.2 as it appears from the figure. So from this equation we can estimate the actual plume height, plume radius, etc. Okay, so let's look at these figures, and that will make it easier for us to understand how we can apply those results into real life plumes. So what you see here is, this one is a lab experiment, obviously, in an stratified medium. Right, and you can see how the plume is injected at the bottom, the dense buoyant fluid is injected, and it rises up, it goes up, the radius continuously increases, as you can see, but beyond this point you can see the radius of the plume just increases to a large value, and that is exactly what we see here, right? This radius that you see, it increases almost linearly to certain height, but after that it increases to a large value, right? And that is exactly what we see here as well, and this is after a certain time. If you continuously increase this dense fluid further, this radius will grow further and further. Okay, so there is no limit for that radius. That will depend completely on how much fluid you have injected into the medium. Okay, it will depend on the time for which the plume has been running. Okay, so that is what you see here, and likewise at this point you can assume that G hat must be equal to 0, right? So the density of the plume must be equal to the density of the ambient. Okay, and that is why it cannot go further up, because buoyancy force is 0, and after some time your momentum force is also 0, or momentum flux is 0, and what all the plume that it can do is it can spread sideward because of the injection that is happening at the source. Okay, so this is how plume behaves in a stratified medium. And if you remember unstratified medium, which is this case, left hand side, if you continuously inject plume, it will just keep going up, right? Because the delta rho is almost never 0. There will always be positive delta rho, and plume will keep rising. But in case of stratified medium, as you look here at the right hand side, your plume after reaching a certain height, it starts flowing sideward, and that we just saw in the derived solution as well. Okay, and now this is a solution we have derived theoretically, and also we have predicted that behavior in the lab. But if you want to apply this solution to a real life scenario, some of the important factor here would be what is the maximum height the plume can reach in an stratified medium, right? So in this particular example, for instance, this is the Z max that it is able to reach, right? And beyond that it's not able to go up, it's actually just spreading sideward, and this is a pollution that we actually get in the cities, or that is what we breathe. If it just keeps going upward, then probably it would not affect us, because plume is just going upward. We are not really worried about the pollution caused by the plume. But when it loses its buoyancy and momentum to further go up, and starts spreading sideward in lower atmosphere, that becomes much more concerning. And this is something we have been discussing, especially during winter. The stratification is more because of fog and other things, and that is why we get even more and more pollution. Okay, all right. So now if you want to predict Z max, for instance, or other parameters, the way we do is Z hat max we have seen here is 3.8. okay, 3.8, that is the value we predicted using the numerical solution. And now we want to convert this Z hat max into the dimensional Z, because Z hat is the non-dimensional part, right? And how we have defined Z hat, that is Z by L. And what is L here? This particular term. So this is L that we defined. So Z hat is Z over L. So Z must be equal to Z hat times L. And Z hat here, we are actually looking for Z max, so that must be equal to Z hat max times L. Okay, and Z max here is 3.8 times L, and L is B naught over N cube to the power 1 by 4. So this gives you Z max for a particular plume. So for a particular plume, I mean B naught is known, and also N is known for the ambient. So if you know the B naught value, which is Q naught times G prime naught, and G prime naught is again defined as rho A minus rho P by rho infinity times G, where rho P is the injected plume density, rho A is the ambient plume density, and rho infinity, for this particular case, you can assume it to be the ambient density at Z equal to 0. So rho infinity is specific to a particular case. How do you define it? Okay, so if you know the B naught value, that is specific to a plume, and N defines the environmental behavior or atmospheric stratification, right? You can predict what is the maximum height to which a plume can reach. Okay, and now you have predicted Z max, you can also predict all other parameters. So if you want to find based on this calculation, if you want to find what will be the reduced gravity or density at a particular height, you can just do that. So let's say if you want to find radius of the plume at Z equal to 10 meter, for instance. So first convert Z equal to 10 meter into Z hat. So at Z hat, see what is your R hat, W hat, and maybe also G hat. And now once you have R hat, W hat, G hat, and that at that particular height, you convert them back to R, W and G, using the formulas that we have derived. Okay, so it is very straightforward, but this is the solution for the plume in a stratified medium.